So I'm going to talk about photo-antimicrobials. Just out of interest, how many people in the audience today have had anything to do with light-activated antimicrobials? Perhaps less than 10, I guess, out of 80-ish. So that's about, I think that's probably about right. It is, as Ern said, it is kind of picking up. Obviously there's a big need for different antimicrobial routes with the kind of dying off of useful antibacterial agents, particularly because of resistance. Just before I start, the meeting of the European Society for Photobiology this year had 2 antimicrobial sessions, which has never happened before. So there is obviously quite a bit more work being done now, which is great. It's taken an awful long time to get where we are. So just to kind of set the scene, conventional antimicrobials such as the penicillins, cephalosporins or tetracyclines, and also the antifungal agents, you can include in that also antiviral agents, they tend to have a single mode of action. So if you look at penicillins, for example, they all act exactly the same site of the bacterial cell wall. So when it's a single site of action and a single mode of action, it doesn't take very much in order to get around that. And then when we have a mutated bacterium, it's more likely that if you've got a single mode of action, a single site of action, then more likely that you'll get resistance. And I'll talk a little bit about that now. So this single site, single mode kind of breeds resistance, encourages resistance. So photoantimicrobials, as we saw earlier, like Alison's excellent presentation, the mode of action in terms of production of oxygen species is exactly the same, whether you talk about anti-cancer or antimicrobial. So if you kind of look at this very simple schematic, we've got a group of bacterial cells. Obviously you have several million, not just a handful, but the ones in the kind of green coloration would have a mutation or an expression of a mutation. And if it was Staph aureus with overexpressed penicillin binding protein 2A, that gives resistance against methicillin. So obviously everything gets killed by the methicillin except these cells. These cells then can go on and proliferate, and you get a resistant population, which is where the danger comes in, and we get mortality. If we use simple photosensitizer and light, then the reaction is completely different. It doesn't make any difference how much PVP2A you've got. You end up with no cells at all. So that's the kind of angle that we're coming from. A little bit more detail. The important part of the molecule in bacteria is what's called dialanine, which is a dipeptide. This exists in the cell wall in order to form crosslink and strengthen the cell wall. So as the cell grows, it kind of stays in a hold really. If you treat it with a typical beta-lactam, which is benzylpenicillin, there's a section of the beta-lactam which is exactly the same as this, and so the enzyme responsible for cross-linking gets kind of confused between the two. You get inhibition of cross-linking, and then you get cell death. The cells will actually pop. You can see quite a few videos on YouTube of how that works. It's quite impressive. However, we have at least 3 different mechanisms of resistance against beta-lactams, whether they're simple beta-lactams like penicillin B, penicillin G. It's called beta-lactamase, which breaks it up. In other words, once it's broken up, it can no longer inhibit by this route. There are penicillin binding proteins, which work against, as just said, against methicillin. So this is where we get MRSA from. More recently, in the kind of late 90s, early 2000s, we had ESBLs, or extended spectrum beta-lactamases, which were in Germany. These are mainly to do with negative bacteria, whereas obviously DVPs tend to be the gram-positives like Staph aureus. Okay, so all of these cause a problem. If we've got these, then we don't get cell death, and the bacteria survive. So in terms of infection, we don't want that. if we have a photosensitizer, either the photosensitizer can be in the cell, the bacterial cell, or it can be kind of stuck to the outside of the cell. It will work in either situation. And this is a very much simpler version of Alison's setup before. Excitation of the photosensitizer, either associated with or inside the cell, leads to the generation of these singlet oxygen molecules here, or the other reactive oxygen species. It doesn't really matter which type. We don't see resistance against either. And we get non-specific damage. So we don't get damage against a single site of the cell wall, or a single site in bacterial DNA, or in the ribosome, or whatever. We get different attack depending on how long you leave the photosensitizer excuse me, to kind of incubate with the cell. So there's a time scale aspect to it. So it's variable and varying activity, all sorts of different sites of attack. It's almost impossible to see how that will lead to resistance. It can't mutate times in order to survive. So that's how we kind of aim to do this. And it does tend to work in most, well, certainly all of the bacteria that we look at, we will kill the whole lot quite simply. Methylene blue is probably the principal, I guess it's the equivalent of kind of HPD at the start of the anti-cancer work. Methylene blue is used in most cases for clinical antimicrobial PDT, which isn't a huge field, as has been referenced already, but it has been around for a while, been around since 1890 in terms of a clinical drug, malaria. We'll talk about that in a while. But if you look through the literature, it was actually described as a photoantibacterial so a very long time ago. And then there was kind of sporadic work throughout the last century. Antiviral, for example, it was shown to be antiviral against the yellow fever virus in 1931. I'm not actually sure why they did that work, but it's there in the literature. And also against protozoa, like malaria, malarial parasite, trypanosomes, all sorts of things like that. So this work is actually out there, and it hasn't really significantly been picked up. So it's quite interesting quite often to go through the literature and find all these different brilliant pieces of work that have been done. So there is plenty of evidence. The major use, I guess, is in kind of oral disinfection by dentists. And as I said this time last year when I was here, the guys out in Brazil using this in all sorts of different ways, but a great many dentists use this approach. So, methylene blue, red light, it's about 660 nanometers thereabouts, interacts with oxygen, produces singlet oxygen typically, pretty good producer singlet oxygen. If that's in or near a cell, then we get photo damage. In terms of current activity, no apologies, I did show this slide last year. Current activity is more or less the same, I guess. So we've got use in treatment of oral disease. We've got disinfection, photodisinfection of MRSA, which I would guess Nick might mention in the next talk, so I won't talk about that. Disinfection of blood plasma has been used since around about the early 90s in Europe, certain states in Europe. And then there's kind of a whole lot of different work done in Brazil. All of this is methylene blue. This is a herpes lesion treated on someone's kind of head. It's around about 4 years now. And this is removal of fungal overgrowth in toenails. So there's lots of kind of examples of this being done by different medics in Brazil. I have no idea why it's taken up in Brazil so much, but it is, it's a pleasure to go there. People actually know who I am in Brazil. So, I'll quickly go through this, I don't want to spend too much time. This is a kind of timescale, various examples of methylene blue and methylene blue derivatives. As you can see, I won't go through all of them, but the very first use, as I said, in malaria, 1890, barbaric. And then this molecule here is quite interesting. Polydon was made in Bayer before the Second World War. This is actually very useful as an anti-bacterial agent as well. So the blue kind of font is to do with photoactive, the red font is to do with just standard conventional anti-microbial. So there are various different ones, different molecules based on methylene blue, which are available, and as we go forward, some of them are getting more kind of preclinical type experimentation. Okay, so toluene blue was used by Mike Wilson down here in London. Both might be here today, but it's not. Huge number of papers on toluene blue in dentistry. Photodynamic from the Leeds, the spin-out company from Leeds Uni, had this very similar molecule to methylene blue. The only difference is in the side chains here. This was used in all sorts of kind of experimentation and clinical trial on leg ulcers, I think it was, but in the end it didn't kind of make it. These two I'm still very suspicious about. I suspect that their dark toxicity is quite high, but again, quite a few groups are using these molecules. And these two, the bottom are in kind of semi-preclinical work. Brazil, mainly for kind of dentistry side. So, activities generally, what we want is, if we want a broad spectrum activity, we need the molecules to be positively charged, so they have to be cationic. So methylene blue, for example, is cationic. The reason for that is if we have gram-negative bacteria, most of the time we see that negatively charged molecules, so this offering thing there, negatively charged molecules don't work very well against gram-negatives. And certainly at the moment, gram-negatives are a big problem clinically. Like Pseudomonas or Klebsiella. One of the huge problems, I'm sure a lot of people have the same problem, is getting this work funded. Typically because if you try and bring a new compound to the clinic, there's a huge long kind of time required and all sorts of different experimentation required as well, and this all costs money. So there's not very much of that around at the moment, whether it's conventional funding from grant authorities or kind of public funding. Also, many photoantimicrobials are better in vitro than conventional antimicrobials or even biocide. And it's quite interesting if you talk to people from the pharmaceutical industry, for example, that you say, well, this works really well, this methylene blue, for example. Works really well, and they say, well, yeah, but that's in a Petri dish. And then you say, well, your drugs don't work in a Petri dish. And then they go quiet. So it doesn't really matter whether we look at standard E. coli or standard staph. It's better to look at things like Klebsiella because it's meaningful. I thought it was meaningful. Klebsiella typically has all sorts of different resistance mechanisms. So it's one of the bacteria which express these extended spectrum beta-lactamases, Klebsiella pneumoniae, carbapenemase is a big problem at the moment. But it also has efflux capability, another kind of protective mechanism, so it's a good target. And obviously, if it's got carbophenamases, all the new expensive carbapenems, ertapenem, meropenem, all these things, these don't work at all. So you're starting off with some very high level of resistance. And you can see here, this is a fairly simple test which showed kind of activity of the butyl toluene blue against Klebsiella oxytoca, which has KPC and is very similar to the NDM1 capability as well, which is a huge problem because that's resistant to all sorts of different drugs. And we can see that we can kill that very simply at a very low concentration. that's not really a difficult test, because we know that's going to work. It's not something that's usually used against Klebsiella. So we thought, well, have a look at something, a combination of a bacterium which is resistant by a certain mechanism against a certain drug, and see if you can change that just by photoactivation. So we looked at Staphylococcus hemolyticus, which is a kind of a standard skin bacterium, but it causes all sorts of infectious disease problems now. If you look at proflavin, which is a very simple, very old molecule, not quite as old as methylene blue, this normally acts against DNA, okay? But it will, in something like Staph hemolyticus, it will be effluxed out. And there's plenty of evidence in the literature that the Noré efflux pump just removes it. If we do this experiment in the dark, we get no kill at all at 100 micromolar, which is quite high concentration, it's about 20 micrograms per mil. Okay, so in the dark, we get nice warms of these bacteria. If we do it with blue light, we get kill at 0.63 micromolar or 1.3 micrograms per mil. So there's a huge difference, and it successfully kills all the bacteria. So what we're seeing there is a standard mechanism which works against the drug. As soon as we photoactivate using the same drug, we get complete kill. So it's a good example of how effective the photodynamic approach can be. So one of the things that we need to classify as a kind of a sector, if you like. How do we use these things? Are we going to use them systemically? We're going to use them topically, and it kind of mirrors really the early anti-cancer PDT work. Topical is going to be the easiest way to go. So we can think of these things really as this kind of surface antiseptics for topical infection. And probably the best idea is to try and treat minor infections, which would quite often go on to be serious illnesses. So things like tonsillitis, for example, which quite often, unfortunately, can progress if you've got resistance to things like meningitis and septicemia. If you use this approach to kill the bacteria when it's at the tonsillitis stage, then obviously you've got an effective prophylaxis. So that's, I guess, the ethos, if you like, going forward. Okay, you can see on this, just to point out, these are traditional antiseptics, and these are some of the new compounds, butyl, toluene, much more effective than standard antiseptics. Okay, just to, I think I've got one slide after this, what might be. Okay, I came across this paper in my rather too brief search of the literature recently. A paper by a Brazilian group used a mouse model, streptococcal pneumonia, and then treated extracorporeally, so they illuminated from outside the kind of chest area of the mouse. Okay, and with the control group, they picked up a Staphylococcus PDT group. Most of them had no bacteria at all. Okay. Because of that, they just went out to 50 days to see what the end result was. They had no deaths in the PDT group, but 60% of the control group died. Okay. This is an amazing paper, but obviously it's produced by a group in Brazil. Nobody sees it. Okay. It's in physiological reports. It's an open access model, so it's worth a look. But this is fascinating work. If we can scale this up, it's obviously a big hit, and we've already talked about the difference between experimental work and clinical. But I think this is probably the way to go. Indocyanine green is active. It's anionic, so it shouldn't be active against gram-negatives. But there may be a different mechanism going on there as well. S pneumoniase is a gram-positive agent. But if it's a photothermal mechanism, which may well be, then it may be possible to treat gram-negative infection as well. So again, go back to Klebsiella, which is a gram-negative, very important in pneumonia, and this might give us a kind of a hint as to what we should do. Just finish off with some nice photographs. I showed these last year. Unfortunately, it's not as close to lunch as it was last year. These are perfectly different patients. These guys are generally fairly poor individuals who can't afford to get their diabetes treated properly. And they eventually present at this clinic run by a guy called Sadibo. He's an absolutely amazing guy. He treats them with methylene blue. The option here, even in this country, would be you kind of take the blood about here. Okay. Usually there's no way back from this. He treats them with methylene blue and red light. Several treatments, but he is actually getting something which looks like a foot afterwards. This patient actually had already had toe amputated. Disease kind of came back, or stayed where it was. And again, you can see it's a kind of an abbreviated foot, but still a foot. You can still use it. The patient is still ambulatory. So there are amazing things. I can't get the NHS interested in this, and I don't know why. Okay, so thank you for your attention.